This is part 10 of the series Three-Dimensional Solids, and I'm going to begin this part with a discussion of a comparison between Euclidean and spherical geometry. Now, the study of geometry can be characterized in two very grotesque categories. One is Euclidean geometry, and that's the subject we've been studying all the way up to and including three-dimensional solids. Three-dimensional solids is a form of non-Euclidean geometry that utilizes Euclidean geometry, but the specific non-Euclidean geometry that we're going to talk about is spherical geometry. There are many types of non-Euclidean geometry, and the one we're going to focus on is spherical, that is the geometry of a sphere. Now let's take a look at standard Euclidean geometry, that is the geometry of two-dimensional space. We start with the idea of points, lines, and planes. A plane is a two-dimensional surface. In spherical geometry, there are no flat surfaces. The analog to a plane in spherical geometry is the surface of a sphere. In Euclidean geometry, we have the idea of the parallel postulate. Parallel postulate says, given a line and a point not on the line, there's exactly one line through that point parallel to the original line. Well, in spherical geometry, the analog of a line is a great circle. A great circle is a circle whose center is the center of the sphere. And so all the points on a great circle are connected by radii from the center to that great circle, but they all go through the center of the circle. Now, if you think of the Earth as having latitude and longitude lines, all of our longitude lines are great circles, but there's only one great circle that's a latitude line, and that's the equator. All the other lines of latitude do not have centers at the center of the Earth or the center of the sphere, and so those would not be considered great circles. So the idea of parallel lines doesn't apply in spherical geometry. Strictly speaking, even though lines of latitude are in fact parallel, they're not lines per se in spherical geometric terms. A line, again, in spherical geometry is a circle that has its center as the center of the sphere. And in triangles, if we look at triangles in Euclidean geometry, we can see we have the standard theorems that apply to triangles. The triangle sum theorem, the sum of the measures of the interior angles of any triangle is 180 degrees. In spherical geometry, on the other hand, the sum of the measures of the interior angles of a spherical triangle is greater than 180 degrees. This angle plus this angle plus this angle are going to be greater than 180 degrees because, as you can tell, these arcs are not straight segments. And a segment in spherical geometry is simply an arc of a great circle. So those are some pretty large distinctions. They sound similar, but there's fairly large distinctions between spherical geometry and Euclidean geometry. And we're going to put those into practice with a couple of ideas. The first idea we're going to talk about is this idea of spherical arcs. So here we have a little bit more detailed sphere, and we're going to talk about this spherical arc. A spherical arc is simply an arc along a segment along a great circle of the sphere. So the arc from here to here is what we're going to be talking about. Now, this is no different than dealing with arc lengths in circles. If you think of this great circle as simply a two-dimensional circle, if we just rotated this on its end, we would have something like this. So you can calculate this arc length just as you would in standard Euclidean geometry to find the measure of an arc length. And that formula is right here. Arc length is to circumference as central angle is to 360, assuming you're in degree measure mode. So here we have a central angle of 56 degrees and a radius of 2 units. So the radius of our circle, our sphere, is 2. That means the radius of our great circle is also 2. So this analogy applies. Because we're dealing with a great circle, that is fundamentally a cross-sectional slice through this sphere, which becomes a two-dimensional object, and we calculate it exactly the same as we would in Euclidean geometry. So I'll go ahead and do that now. We have arc length is to circumference, which is 2 pi r, radius is 2, as the central angle, 56, is to 360. Now that's all we have to do to solve for arc length, is multiply both sides by 2 pi 2, which is of course 4 pi. So arc length is 4 pi times 56 divided by 360. And again, I would enter this as a chain calculation if you wish. Put another set of parentheses around this, but it's not necessary because this is multiplication and division, and so we can just enter it directly. So let's just go ahead and enter it here. We have 4 pi 56 divided by 360 gives us 1.955. So that's approximately 1.955. And that is arc length. It doesn't really get a whole lot more complicated than that. If you wish to find the length of this arc, you could simply take this and subtract it from the circumference, or you could take this angle, subtract it from 360, and redo the calculation. Instead of 56, it would be 360 minus 56. Up to you how you want to do it, but it's the same as what we did back when we were in circles and talking about arc length of a circle. And now the next topic we're going to talk about is spherical triangles. Here we have a basic spherical triangle. Notice that each side of the spherical triangle is an arc of a great circle. And you'll notice also that if you sum these angle measures, 105 plus 95 plus 98, that comes out to 298, which is clearly greater than 180. So that's a fundamental theorem, the idea that the sum of the measures of the interior angles of a Euclidean triangle is equal to 180. The sum of the measures of the interior angles of a spherical triangle is always greater than 180. And if we want the area of a spherical triangle, we would do this calculation. Remember that the area of a triangle in Euclidean geometry is 1/2 base times height. This is significantly different than that. We have pi r squared, which is the area of a circle, divided by 180 times the sum of the interior angles of the spherical triangle minus 180 degrees. So that is the basic formula for area of a spherical triangle. And if we wanted to actually apply that in this problem, we would simply plug in our values. So we would have pi times 7, 7 is the radius, divided by 180, times angle 1 plus angle 2 plus angle 3, so 95 plus 105 plus 98 minus 180. And again, I would go ahead and calculate that as a chain calculation, and my result is going to be 100.91. And that is spherical triangles. Well, I hope this was helpful for you, and that will wrap up the series on three-dimensional solids. I hope it was productive, and I will talk to you in another video.